Hello and welcome to another chemistry topic together. Our focus today, as you can see, is gas laws. So, would you please start setting up your focus note page? If you're doing this on the day it was assigned, it is March 1st. Otherwise, fill in whatever date it is that you are watching this. And your essential question for today is what are the relationships between mass and temperature and pressure and volume of gases? So, gas laws is our focus. And just so you know, this lecture does not cover every gas law that's out there. We're going to focus on one that kind of has a whole bunch of the different relationships that I want you to be aware of. And then if there were different equations that you might learn in a different chemistry class, you would still understand how to use those gas laws, what the variables are, and what the relationships are, even though we're only focusing on one gas law math equation. All right, pause the video if you need more time setting up your focus notes. Otherwise, let's get into it. So, one of the things that gas laws have is lots of variables. So, we got to talk about some different letters that you need to know if you see them in equations or in problems or data, what they refer to. So, a capital P is dealing with pressure. So, you possibly remember we talked about that kinetic molecular theory says that all particles are made of or all matter is made of particles, and those particles are always moving. When we think of gas particles, the motion of those gas particles colliding is what causes pressure. So that's a very important term or vocab term to think about when we're talking about gas laws. Your pressure could be measured in ATM or atmospheres, millimeters of mercury. This comes from the idea that there used to be old fashioned barometers, which measure pressure, had like a tube upside down in a dish of mercury. So the pressure around that dish of mercury would push on the mercury. And then, depending on how much mercury went up the tube, that would be how much pressure there was. So that's where millimeters of mercury comes from, or kilopascals, another unit of pressure. So I just want you to be aware that if you see this label on a number, that is a unit of pressure. Capital V stands for volume, thinking about how much space a gas is using up. Milliliters or liters would be the units for that. And then capital T is temperature. Now, for gas laws, you do have to convert your temperature into Kelvin. And why is that? What do we know about Kelvin that maybe would be useful for math equations? Can you think of it? There's no negatives, remember, because you can't go slower than absolute zero. So you can't have a temperature less than negative or in a negative range for Kelvin. Side benefit, it usually gives more sig figs also. But the point is that what your temperature is probably going to be measured in Celsius for lab data, because we don't have Kelvin thermometers, at least not in our data labs. So you'll have to convert the Celsius temperature into Kelvin for gas laws. So just be aware of that. All right, so for converting, for pressure, we know that 1 atm equals 760 millimeters of mercury equals 101.3 kilopascal. These things are all equal to each other, so you can use these as conversions to go between any units that you need to. We consider definitions, which means that doesn't count for sig figs. So if you are given a unit of atm, but the problem is asking for a unit of kilopascals, you can use dA to convert that. And these are considered definitions, so this is not just one sig fig, this is exactly one as many sig figs as would be needed. For volume, just a reminder, there's 1,000 milliliters in a liter. So again, if you were given milliliters, but the problem was asking for liters, you would be able to convert that. And for pressure and volume, the units just need to cancel within the problem. So it doesn't always have to be ATM. It doesn't always have to be liters. However, your units need to cancel. So you need to check that. So make sure you label your numbers. For temperature, remember, if we're going from Celsius to Kelvin, which is normally what we're going to need to get Kelvin, you take your Celsius plus 273. So that will be your Kelvin temperature that you would then plug into your gas laws. All right. Okay, another set of letters that we'll use sometimes, just a reminder, is STP. Standard temperature and pressure. So if you see that in a problem or talked about in a lab situation, that means a specific number, a specific temperature, and a specific pressure. Standard temperature is 0 Celsius or 273 Kelvin. Standard pressure is 1 atm, which is also 760 millimeters of mercury, which is also 101.3 kilopascals. So a bunch of variables, P, V, T, STP, things you should be aware of when you're learning or thinking or studying gas laws. Go ahead and write a level 1 question, pause the video, take a little break, process what you just read. You can use your Schoology handout guide that gives you Costa question sentence starters, or make up your own. The general idea are things like list or define, something that comes right from the notes. Pause the video, come back when you're ready. All right. The next thing I want to talk about is ideal versus real. Now, this is very similar to when we talked about actual versus theoretical. We just use the terms ideal and real when we're talking about gases. An ideal gas does not really exist. So, like ideal, like in theory, it ignores the fact that gas particles have some amount of volume and that there is some amount of attraction between gas particles. We ignore that because it makes the calculations a lot simpler. So, really, an ideal gas is in theory. We use ideal situations a lot of times so that we can study things and we can ignore certain variables that just make the math a lot more complicated. Then we can come up with ideas to apply in a lab setting, knowing that there will be a small amount of error associated with it. However, the error is very small, and so it's not a huge problem. So, this is a disclaimer slide that I want you to be aware that, especially if you take AP Chem or some other college chem class, you'll learn about the volume of gas particles in gas laws and the attraction between gas particles, and you'll learn how to correct for that. But for pre AP Chem, we can kind of ignore that for now. So, real gases is what we actually observe. It's in experiments, in lab. And the great news is that most real gases follow gas laws, the ideal gas laws, at most temperatures and pressure. So, again, it's not like a huge cheat to ignore the things that we ignore for real gases and still get answers and calculations. It's still a good conclusion. So, we use gas laws ideally because most gases follow the ideal gas laws. All right. Go ahead and do a level 2 question. Maybe, compare and contrast ideal gases versus real gases, or what does a real gas have that ideal gases don't? I guess that's kind of a level 1 question because it was in your notes. Anyway, pause the video, do a level 2 question, come back when you're ready. So, speaking of ideally in gas situations, here is the ideal gas law I want you to be familiar with. PV equals nRT. Pressure, volume, temperature. Oh no, 2 more variables. What are N and R? Okay, so the last 2 variables you need to know are N is the number of moles. Wait, moles? Guess what time it is since moles come back? Okay, what is Avogadro's favorite drama movie? No, this is kind of an old one, but you may have seen it. If not, you should check it out. It's with Tom Hanks. It deals with a prison guard. Have you heard of it? It is The Green Mole. You should check it out. It's a really good movie. And then, what is Avogadro's favorite fruit? Now, you wouldn't be able to find these probably very much in season right now in Minnesota. However, he loves watermelons, of course. All right, so N is the number of moles of whatever gas you're dealing with. So just realize if you're given grams, which is more practical, you're going to have to convert it into moles to use the ideal gas law. And then R is a constant. It's named after some guy named Rulberg. I don't want to remember his first name is, Mr. Rulberg. And he did a whole bunch of experiments. So this does count for sig figs. And he came up with a constant, meaning that anytime you see R, you plug this whole thing into R. It is 0.821 liters and atmospheres over 1 mole per 1 Kelvin. So it's based on a whole bunch of different gases and different volumes, different amounts of gases, different amounts of or different temperatures of gases, and a bunch of experimentation to figure out that if you use PV equals nRT and you plug this number in for R with these units, you can solve for everything else. So, named after a guy who did a whole bunch of experiments on gases, that's where R comes from. All right, now let's talk about the relationships within PV equals nRT. How are these variables related, which will help us also understand some more things about kinetic molecular theory? Let's focus on pressure and volume. All right, pressure and volume are on the same side of the equal sign, meaning that if one goes up, the other has to go down to keep this equal. Well, let's see if that makes sense. If the pressure is high, the volume is low. Well, remember, pressure is considered collisions, right? And if the volume is low, that means there's not very much space. So the gas particles are more likely to collide. So yeah, that means pressure would increase. And the opposite. If the volume is really high, the particles are less likely to hit each other. So there's less collisions. So then the pressure would be low. That is an indirect relationship. How about between pressure and temperature? Pressure is measuring collisions, temperature is measuring motion, okay? They're on opposite sides of the equal sign, so when one goes up, the other goes up, a direct relationship to keep this mathematically equal. Pressure is high, temperature is high. So again, does that make sense? Temperature is a measure of motion and energy. If there's a lot of motion and energy, there's going to be a lot more collisions, which means the pressure will be higher. So, yeah, that does make sense. All right. How about between volume and temperature? Once again, these are on opposite sides of the equal sign. So, if I'm going to keep this mathematically equal, when one goes up, the other would also have to go up. That is direct relationship. Let's see if that makes sense. All right, so temperature is again a measure of motion. If there's a lot of motion, the particles are going to move more. And if they move more, they'll take up more space. So increase volume when the temperature and the motion is higher. And the opposite, if the particles are moving really slow, that means that they're not going to take up as much room. And so that means the volume would be lower. Direct relationship. How about pressure and moles? All right, well, pressure and then moles, remember, is N, opposite sides of the equal sign. So we've already seen that probably means direct, but let's think about why. So if there's more moles, there will be more pressure. Does that make sense? Well, yeah, because if there's more moles, that means there's more particles of gas. And if there's more particles of gas, they're more likely to hit and collide, which means there would be more pressure. And all the opposite is true, direct relationship. One more little side relationship that's not in the equation is just the relationship between kinetic energy and temperature. I just want to make sure you see that connection. So kinetic is the energy of motion. Temperature is measuring that motion. So it's a direct relationship. If there's more energy, it's a higher temperature. So I just wanted to make sure that was obvious since we're talking about relationships. Kinetic energy is not a thing you plug into this equation, but it is something we've talked about earlier this unit, and I just want to make that connection. All right, so with all those relationships down and a whole bunch of variables down, it's time to finally do some examples. This could be an example that you might have in lab. Determine the volume occupied by 2.34 grams carbon dioxide at STP. All right, well, here's the good news. We only have one gas law, PV equals nRT. The problem says determine the volume. So I know I'm solving for V. So I do some algebra. I need to divide both sides by pressure to get volume by itself. So then pressure would cancel here, and then I would have V equals nRT divided by pressure. That's the equation that I'm using. So then I'm going to make a list of what I know. So do I have a pressure? Yeah. 1 atm. How did I know that? Because it says standard temperature and pressure. And remember, standard pressure is 1 atm. Yeah, it's also 760 millimeters of mercury or 101.3 kilopascals. But remember the units of R? I'm saving myself some work just by starting with 1 atm. All right, how about V? Well, that's what I'm looking for. How about N? Well, N, remember, is moles, but I gave you grams. Hey, we can fix that. 2.34 grams of CO2. Where did CO2 come from? Carbon dioxide. And so I want to convert that into moles. So I need to find the molar mass of carbon dioxide from the periodic table. Carbon is 12.01, oxygen is 16 times 2, add it together, 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide. Grams of carbon dioxide cancels. I'm ready to solve moles of carbon dioxide. Multiply on the top, divide on the bottom. This is not a final answer, so I'm going to number dump. So this whole thing is what I'm going to keep for now, my moles of CO2. All right, so now I've got moles, PVN. R, remember, is a constant, 0.0821 liter atmosphere over mole Kelvin. So this is why I had to get to moles. This is why I had to use ATM instead of using something else. And then for temperature, I'm going to use 273 Kelvin. Where did I get that? It says standard temperature. Standard temperature is 0 degrees Celsius or 273 Kelvin. Because remember, getting from Celsius to Kelvin is Celsius plus 273. So standard temperature is 0 Celsius. It's 273 Kelvin. And why do I use that? Because remember, your units have to cancel within your problem. All right, so now I'm ready to plug stuff in. So V equals nRT over P. So N was 0.053169 moles. R was the constant with all those labels. T is 273 Kelvin divided by pressure, which is 1 atm. Let's check our units. Moles and moles cancels because you have moles on top and then divided by moles here. You have liters on the top here. Oh, liters doesn't cancel anywhere. Oh, that makes sense because I'm looking for volume. I have ATM on the top here, ATM on the bottom. That cancels. I have Kelvin on the bottom here and on the top here. So Kelvin cancels. The only thing you're left with is liters. So I multiply these numbers, technically divide by 1. I can keep 3 sig figs because this has 1, 2, 3. This has 1, 2, 3. I plug it into my calculator, solve, round 1.19 liters of carbon dioxide. Pretty small amount of liters, but it makes sense because the temperature is pretty cold and the grams is pretty small. So it makes sense that it would not take up a very big amount of volume. Ideal gas law example. Let's do one more. How about this one? At what temperature will 0.654 moles of neon gas occupy 12.30 liters at 1.95 atmospheres? Okay, remember, it's good news is we only have one gas law. PV equals nRT, but it's asking for at what temperature. So I need to solve this for T, which means I need to divide both sides by NR so that it cancels here and leaves T by itself. So T equals PV over NR. All right, let's make a list of what we know. Our pressure was given atmosphere, that's a unit of pressure, 1.95. My volume was given liters, that's a unit of volume, 12.30. N was given moles, 0.654 moles. R is a constant, so I always have it, 0.0821 liter atmosphere over mole Kelvin. And T is what I'm looking for, at what temperature. Plug your variables in, make sure the units cancels. So 1.95 ATM pressure, 12.30 volume, 0.654 mole, that's N, and then R is on the bottom. So atmosphere is on the top here and on the bottom there. Liters is on the top here and on the bottom here. Moles is on the top here and divided by moles over here, and I'm left with K. That is a unit of temperature, so I'm ready to solve. Multiply on the top, divide, divide. It looks like I can keep 1, 2, 3, 1, 2, 3, 1, 2, 3 sig figs. So when you get the answer on your calculator, round it off, 444 or 447 Kelvin. All right, so then that would tell me some stuff about neon. What it would have to be that hot before it could fill up this much volume and have enough energy to move around and fill 12.30 liters. So, some information about gas laws and kinetic theory and energy and relationships between gases and what the particles are doing. And that brings us to the end. So write a level 3 question. I would love one about predict when I might need to use the ideal gas law or how it might be useful. I'll give you a hint. Think hot air balloon. Maybe I would need it for that. Okay. Well, actually, hot air balloon's not, well, no, that could work. You could write a question about that. Anyway, write a level 3 question, pause the video, come on back when you're ready. That brings us to the end of our third day and the last day of this unit for this try two during pandemic distance learning. Go back and finish any Costa questions if you did not already do them, and then write your summary for today's notes, which should answer your EQ. And then to practice this new information, I want you to do a gas law video lab. So the video lab is on Schoology, the handout is on Schoology, take data, and you just have to finish the handout for your lab report. So you don't have to start from scratch and write a full report, just finish the handout. And then if you're watching this video when it was originally assigned, this is your last thing for this trimester, and the end of the trimester is Thursday. So finish this lab handout by Thursday. And then that's the end. That's the end of Chem B or Chem A. So I'm excited to work with you next trimester for pre-AP Chem B. I do recommend that you save everything from Chem A. You just don't know what you might want. Notes and handouts and guides and those kinds of things. Just save everything so that you have it if you need it. All right. So thank you for exploring gas laws and gas law relationships with me and the ideal gas law. And for those of you that are watching this again on the first time it was assigned, thank you for your work this trimester. I'm excited to keep working with you. If you're watching this video at any other time, thanks for joining me, and we'll talk to you next time.